All right, so let's move on to chapter 20. It says the micro-macro connection. Micro-macro, yeah.
So like, is there no equation for like convection or anything?
No.
Like,
I mean, it's a complicated process. It's similar to like diffusion, probably.
so it's like you don't just go through this course?
Probably, yeah. I mean, it depends on too many variables.
Oh.
Yeah, yeah, yeah. It's, I would say it's similar probably to diffusion. Yeah. So let's erase this. Yeah, so the only, so convection we don't have, at least, not at the moment, yeah. But yeah, definitely you can predict if I set a heater there, you know, what is the temperature over there as a function of time based on the dimensions of the room, probably, how much air there is, and so on.
Oh, yeah.
So again, we're in chapter what again? 20, yeah. So finally, we're going to look under the hood, right? You go to the actual gas and look at the molecules, and you want to know what's going on in there, right? We always said the gas inside the piston, and you get pressure, temperature, you got some energy, number of molecules or number of moles. So what's going on in there? So first, I'll just read this. It says, chapters 18 and 19 focused on the macroscopic picture, the large picture, of state variables such as volume, pressure, temperature, and specific heats. And now we're going to ask, what are the little molecules and atoms doing? So it starts with the following: molecular speeds and collisions. So how fast are the molecules in this room of the gas moving? Are they all moving at the same speed?
No.
They're not. Some of them are moving faster than others, but there is a distribution of all the speeds, how fast they're moving. Some speeds are more probable than others. I mean, how many molecules do you think would be moving at or near the speed of light? Very few, yeah. How many of them would be moving at speed near zero? Probably very few. So, so somewhere in the middle, it depends on the temperature, it turns out. And so you have a distribution. It's called. I might do a worksheet on this, maybe not. I don't know, time permitting. So it says here.
Do it. Yes, sir.
Let's see. Yeah. Here are the speeds, and then the percent of molecules moving at that speed. Percent of molecules moving at that speed. So it looks like this. It's a function that's kind of left-leaning. Okay. So you got a most probable speed. You got the average speed somewhere here based on that function. You got the median speed, and so on. So once you know the function explicitly, you can figure out what it does. So, so let's say speeds between 0 and 100. So let's say these are the speeds between 0 and 100 meters per second. Maybe these are the speeds between, let's say, 200 and 300. Maybe these are the speeds between 400 and 500. They're more probable. So based on the temperature, you can predict which speeds are most likely to be, more molecules will be moving at that speed. The exact form of the function based on the number of molecules and so on, it's called the Maxwell-Boltzmann distribution. And it looks like this. The function itself, let me Yeah, let me write it. The distribution of all the velocities, V for velocity here. V for velocity. It looks like this. 4 pi n. N is the number of molecules. And then the mass, it's like, yeah, let me write it. Mass, and then 2 pi kb. kb is Boltzmann's constant, right? And then capital T is the temperature. And then this thing to the power 3 halves. Okay? To the power 3 halves. And then v squared, v for velocity again, or speed. And then e exponential to the negative, yeah, m v squared over 2 kb times t. Okay? So, yeah, so if you have a computer, you can go ahead and plot this function. You can, let's say, select a certain temperature and then go ahead and plot it. 4 and pi and n and m and k and t, all of these are just a constant. Once you set the temperature, it's a constant. And then you can have plot this function, v squared e to the minus something times v squared. It will give you something like that. And the higher the temperature, the peak will move to the right or to the left if the temperature gets higher. To the right, yeah. The higher speeds will become more probable, right?
Mm-hmm.
Yeah, the higher speeds will be more probable. Yeah, so the macro connection is built on the idea that macroscopic properties, they arise from what the microscopic things, the atoms are doing. So what the little individuals are doing affect the overall behavior. Okay, so now the mean free path. So as a gas molecule moves from point A to point B, does it move uninterrupted or does it collide? Yeah, collide. In fact, it collides a couple billion times per second. So the mean free path looks like this. So let's say my gas molecule has looks like this, and it has a radius r. So let's say this is r. Just trying to motivate what the author shows. He does a calculation. So let's say it's going from this point to this point. All right? So a length L from here to here. Will it collide? If a molecule is here, if another molecule is here, is it going to collide with it? If it's moving just this way. No, it's not within its path. If that molecule is here, will it collide with it? Yes, because it's there. So as long as the molecule is here, they're not going to collide, unless it comes within what? So it basically has like a tunnel. It has a tunnel of this width, where it can move uninterrupted. Right? It can move like that. So, does that make sense?
Mm-hmm.
Yeah. Okay. And what's the radius of this tunnel here? So this is R, and this is R, and we assume all the molecules have the same size, or all the atoms are the same, right? This is R, this is R, this is R, and this is, so 2R, right? This is 2, the whole thing is 4R, so this is 2R. So I basically have, let's say my molecule moves in a cylinder that is 2R. At the end, I'm going to give you just a formula that what we get is not even an exact result. A more estimate is given, and that's what we have to. Later derivations will be more important than this one. This one we're trying to motivate. So as long as you understand that we have a cylinder here, radius 2r and length L. That's good. Okay. Yes.
So if anything is in the cylinder, it hits molecule? Is that what you're
Yeah, so if it's within the cylinder, it will hit it. If it's outside of the cylinder, it's going to not hit.
Okay.
And the idea is this: if within this volume of cylinder, how many atoms would there be, would likely be? So that if there are 10,000 atoms, it will collide 10,000. So we need to know the number density. So that's the idea. So lambda is the mean free path, meaning how long will it move and then without colliding. So the mean free path is called lambda. So lambda will be the path length divided by the number of collisions, COLL means number of collisions. So if it moves 1 meter and it has collided 10,000 times, it means it has moved 1 over 10,000ths of a meter freely, and then every 1/10,000th it collides, right? Does that make sense?
Yes.
Yeah? Okay, all right. So that's that, right? Now, number of collisions, how many collisions are there? Well, number of collisions will equal to the number of atoms per unit of volume. So how many atoms will it encounter here? So let's say the number of atoms per unit of volume, and then times the volume of this cylinder, that will give me how many atoms will there be within this cylinder. Okay? So times the volume of this cylinder, right? So let's say I have 1 billion atoms per cubic meter. 1 billion atoms, 10 to the 9 atoms per cubic meter. And I have a cubic meter cylinder. So how many atoms would there be?
Sit on with that?
Yeah, so let me say. So 1 billion atoms per cubic meter, right? 10 to the 9 per cubic meter. If my cylinder happens to be 1 cubic meter, how many atoms would there be on it? 1 billion, yeah. How about if my cylinder happens to be half a cubic meter? It will be half. So that's why I'm multiplying by this proportion. So if the volume of the cylinder happens to be equal to V, then it will just, the number of collisions will equal to the number of atoms. So now, number over V times, what's the volume of this cylinder?
Pi r squared times h.
Yeah, it's pi, and by r you really mean 2r, right?
Oh, yeah.
Yeah, 2r squared times h, and by h we mean the length of this cylinder.
So Professor, why did you add that extra r, basically? Added like...
Yeah, so we said it will, anything, so this is our atom moving.
Yeah.
If the other atom is here, it's fine, it's not going to collide with it. But if it comes within this distance, then they will collide, right?
Yeah.
Yeah, so it will move uninterrupted as long as it's within this kind of cylinder, like that.
Oh, okay,
Yeah,
so
that's
it's
why
not
it's
in front of the, okay.
Yeah.
That, you're saying that the middle atom will move uninterrupted, right?
Yeah, the middle one, yeah, the middle one, yeah. I mean, of course, when it collides, it's sometimes going to change direction, right? It's going to probably bounce backwards. But this is just a rough estimate, yeah.
Why do you put half of the circle above the center circle? Why can't you just put like a little bit?
Let's say half of the circle.
Yeah, you put half of it inside that.
So this is the minimum. This is the minimum. If it's farther than that, it will definitely not collide.
Yeah, it's kind of confusing, but I got it.
Okay.
So like, what if you
Like, think about it like your car and your side view mirrors. Like, your side view mirrors aren't the car, but if you rush into somebody's
I
side
like
view
that.
mirrors,
I like
it's
that.
still gonna you're still gonna feel that.
Yeah. I like the side view mirror thing. Yeah.
The side view mirror is an extension of the car. It's
Yeah.
not the car.
But
So-
it's not critical to
Yeah.
that.
Yeah.
Well, so many falls in front of it.
So the lane of your car, right? That's like putting. Maybe I'll try to. Here's the deal. Let's do this, Enrique.
Yeah.
the book has a nicer picture than the one I'm drawing. Take a look at it, and then we can discuss it further.
Okay.
Yeah, that's why I like the PowerPoint, but I wish I didn't. I'm not the best artist, but yeah, probably near the worst. Yeah.
So the minimum, so if what we're trying to say, I think, is that a molecule has to be 2 radii away minimum to not collide with another, molecule.
It has to be 1 radius above and 1 radius below. Yeah, so 2. Yeah.
Oh, okay. But we're talking about like the center of each molecule has to be a minimum of 2 radii
Yeah.
away.
Yeah.
Okay, yeah. That makes
So,
sense.
okay.
Yeah.
So, I think the book has nicer, definitely nicer pictures.
It might be like something.
And again, this is an
Like the number of
estimate.
atoms in
We're trying to just get a number. We're trying to get what is it called? A relationship. Or, yeah.
What is the V on the bottom of the collision?
Oh, yeah.
Yeah.
So, we said the number of collisions will equal to the number of atoms per volume. We call, let me see here. V for volume, V for volume, and this is the volume of the cylinder. Okay. So I think it's confusing that there is a V here and a V here, right?
Yeah, well, I'm confused, like,
Yeah.
because what other volume is there other than the cylinder? The volume of the molecule?
Oh, so the gas is in a certain container, right?
Mm-hmm.
So there is the volume of the container. How many molecules do I have within this enclosed volume of gas?
Oh, okay, that makes sense.
Or within this container? And within that container, the gas molecules are moving. And we're just creating this imaginary cylinder or path for the gas molecule to move.
I'm just thinking about side view mirrors.
Okay. Yeah, freeway lanes. So, okay, but that was a good analogy. I really liked it. I'm going to borrow it next time when I explain. Okay. So we got this, and I wanted to discuss pressure also. So the number of collisions will be the number per volume, and then the volume of the cylinder then will be, when you square the two, you get the 4 pi r squared times L. And R is what again?
R is the
Radius
two R.
of? Is it the radius of the
The
cylinder?
molecule.
Yeah, it's the radius of the molecule. Yeah, the cylinder is 2r. Yeah. Okay, that's the number of collisions. And we're going to substitute that in here. So I will have L over the number of collisions. So let's do L divided by this. What do I get when I divide L by this? If you put this whole thing in the denominator.
V over N
1 over
4 pi r squared.
Okay, so you get 1 over, because an L on top cancels this L, and you have N over V, right? And then you'll have 4 pi r squared. Okay. Now, if you want a more exact form, so a more exact form, so this is a motivation. So let's say you don't get this analogy. It's just, let me give you just the correct answer, the real answer, the exact, or the more exact. It's never exact because we're always averaging. I mean, every molecule will do something different. It's very similar. The important thing is it depends it goes as the number density N over V is in the bottom. That's the important. And where is that? It looks like this. Lambda is 1 over, okay, that's fine. And then we had the 4 times pi, right? 4 pi, and then N over V to the power, times R squared, right? This is what we have. This is what we have from here, right? That's the one we derived using a really simple model. Really complicated model and more exact, just adds a square root of 2. And the square root of 2 is like 1.4. So it's almost exact. We're off by just a factor of 1 over half of 2. So, I will just box this one.
Should we have it with the square root of two?
Huh?
Do you want us to have it with the square root of two?
Yes, so that's the actual. Yeah. This is a motivation for it, and then this is where it's. Let's, here's a, let's do a calculation, all right, let's do a calculation. It says, suppose, or what is the mean free path? This is the mean free path, right? Mean free path. What's the mean free path for nitrogen molecule at 1 atmospheric pressure and then a room temperature of 20 degrees Celsius? So, so let me write it. Find lambda for a nitrogen molecule. So for an N2 molecule, okay, the mass, we will write it in a second. Molecule. Yeah. At P equal to 1 atmosphere and T equal to 20 degrees Celsius, so 293, right? And I wish the author would have chosen another molecule besides N2, besides nitrogen. Why? Yeah, we have the number of molecules is also N. It's the symbol N. And nitrogen has the symbol N with it. Maybe oxygen would have been a better choice. I don't know. Anyway, so nitrogen, okay? So lambda, I need this N over V, right? And R. And they say use R for nitrogen is about 10 to the minus 10. So use R is about 10 to the minus 10 for nitrogen. So let's say it's 10 to the minus 10. So how am I going to do this? So lambda will equal to 1 over 4 square root of 2 pi, all these are just numbers. And then N over V, and then R squared. R is 10 to the minus 10, right? So now N over V. How am I going to get N over V?
Like you and gas law.
I did that. Yeah. So PV equals to, since I want capital N, right? So I will use the other one, the other for NKB times P, right? We usually use nRT, the number of moles, times R. But since this one explicitly wants the number of molecules per volume, so I want to use this formula. Okay? Use this. So that means divide both sides by V and then divide by KBT on here, so you get this. N over V is equal to pressure over K B times the temperature. So that's N over V. So let's calculate N over V. The pressure is 1 atmosphere. Is atmosphere good to make the calculation? Yeah, we need the 1.013 times 10 to the 5th. What was Boltzmann's constant?
5.67 times 10 to 8.
It's actually 1.38
Ah,
times 10 to
oh, the other one.
minus 123.
And they're both Boltzmann.
Yeah. Boltzmann's name is all over thermodynamics. Yeah.
He's really smart, they should name geniuses after him, call him a Boltzmann brain.
So we have the temperature 293, right? 293. So as you expect, I mean, the number of atoms per cubic meter would be a lot, right? So
Yes. Oh, yeah, because there's negative.
yeah, cubic meters. So do that, you would have like 10 to the 28, so about 10 to the 26 probably. So about 2.5.
Yeah.
times 10 to the 25th, right? Per cubic meter. Molecules per cubic meter. It's a number. Okay, so now we go ahead and substitute this here. So 2.5 times 10 to the 25th. 2.5 times 10 to the 20 times 10 to the 25. And so the number of the mean free path will be tiny, right? It doesn't move very far before it collides. And that turns out to be about 2.3 times 10 to the minus 7. 2.3 times 10 to the minus 7 meters. That's how far it moves. So we said the radius is 10 to the minus 10, so it moves about a few thousand atoms and then it collides again, right? A few thousand atoms. Yeah,
What are the units for number again? Just meters?
yeah, just meters.
Oh, okay. Oh, that's a tab,
It's
okay.
it's a fact, yeah.
Okay.
Yeah. I guess I will start here next time. I will stop. I will give you your quizzes back. For people who are going to meet me right now, I will give you your quizzes there. For the other section, I will give it to you now.